This video will cover Chapter 14, Section 1, where we'll learn about correlation coefficients, how to calculate and interpret those, and determine whether a correlation coefficient is statistically significant. We'll start off with a reminder here. A scatter plot or a scatter diagram is a way that we show relationship between two quantitative variables. The correlation coefficient measures the strength of the linear relationship between two variables. The number simply measures the strength. It does not imply causation. It doesn't tell us that one variable causes the other variable to change. And in fact, sometimes when we see correlation, that correlation is actually what's called spurious correlation, which means that two variables appear to be correlated, but in reality, they're not actually related. So in our scatter plots here, we see a positive linear relationship between x and y in this first graph. Notice how x starts out small and so does y, and as x gets bigger, y gets bigger, and we have this approximately linear positive relationship. In the second graph, we also see a linear relationship. It's a negative linear relationship. So as x increases, y decreases. Graph C shows a curve linear relationship. If we were to approximate this, we would get sort of a curvy line, and that would have a negative relationship between the x and the y. In graph D, we see a positive but curved relationship between the x and the y. In graphs E and F, there's no relationship between x and y. To calculate the sample correlation coefficient in an attempt to describe our population correlation coefficient, we will use our sample data and we'll calculate something that we call the R. Notice that's a Roman letter, so it represents a sample statistic. We calculate this by looking at all the variation in the x's about their mean times the y variation around its mean, and divide that by the variation in the x's squared, the variation in the y's squared, and square root of that. We're going to use Minitab or Excel to get this number for us. When we talk about this sample correlation coefficient, it's actually unit-free, which means we can't apply any particular units to it. The values range between -1 and 1. The closer to -1 we get, the stronger the negative linear relationship is. And in fact, if we get -1, those two values move in perfect lockstep with each other in the opposite directions. So as x increases, we can perfectly predict what's going to happen to y, how much y is going to decrease. The closer to 1 we get, the stronger the positive linear relationship, so the two variables move in the same direction, and if we actually got a correlation coefficient of 1, we could perfectly predict how much y is going to change each time we change x. If we get 0, there's no correlation between the two variables, and the closer to 0 we get, the weaker the linear relationship between the two variables. So the first graph shows us an R, or a sample correlation coefficient, of -1. You notice y is a perfect linear function of x. For each unit we change x, we can predict what's going to happen to y. The second graph shows us an R of -0.6. So we see those dots close-ish to the line, but not perfectly on the line. So there's a negative correlation, but it's not perfectly negatively correlated. The third graph shows us a sample correlation coefficient of 0. So x and y do not appear to be related at all. This fourth graph here shows us a positive sample correlation of 0.3. Notice the dots are further away from the line than they were in our -0.6. So it's a weaker relationship, it's closer to 0, but it still seems to be slightly positive. And then if we have a perfectly positively correlated set of variables, we're going to get a correlation coefficient of +1. And notice as x changes, we can perfectly predict what's going to happen to y. All the dots lie exactly on that linear function. So let's look at an example. Suppose we're interested in the correlation between tree height and the tree trunk diameter. And we have a sample here where we've got 35 feet and 8 inches. That's one tree. We've got 49 feet and 9 inches, and so on. To do this by hand, we really just multiply those together. We square the y, we square the x's, and we add up all of these columns. And we plug them into the formula here. This gives us a sample correlation coefficient of 0.886. 0.886 tells us that there's a strong positive association between x and y. And actually, if we look at our graph and were to try to draw a linear function in here, these dots lie fairly close to a line that we could draw approximately in the middle of those dots. So there's a strong positive linear relationship between trunk diameter and tree height. The bigger the trunk diameter, the taller the tree. We can also do this in Excel or in Minitab. So in class, I'll show you how to do this in Minitab. In Excel, we'd go to Data, Data Analysis Correlation. We'd highlight in the two columns of of interest, the tree height and the trunk diameter, and this will spit out that same value that we just saw. So this is actual Excel output here. The trunk diameter as it relates to tree height is 0.886. You'll notice ones on the diagonal because tree height is perfectly correlated to tree height. Trunk diameter is perfectly correlated to trunk diameter. The values of interest in the Excel output are always the values beneath the diagonal of ones. We can do a hypothesis test for correlation. When we do a hypothesis for correlation, we use the Greek letter rho to represent the population correlation coefficient, and our null hypothesis is that there's no correlation between the two variables. So we start out by assuming that rho is equal to 0. We're attempting to prove that those two variables are correlated to each other, so our alternative hypothesis is that that correlation coefficient is something statistically different from 0. If we're able to reject the null, we're able to say the two variables are correlated to each other. To do this hypothesis test, it's actually a t-score, and the t-score is calculated as follows. We take the sample correlation coefficient and divide that by the square root of 1 minus that same correlation coefficient divided by n minus 2. N minus 2 degrees of freedom because we're estimating two sample means in this process, the sample mean of x and the sample mean of y. So let's look at our example of tree height and trunk diameter again, and let's perform the test to see if these are statistically significant to each other at the 5% level of significance. We'll calculate our t-score. Our t-score is 0.886. That was our sample correlation coefficient, divided by the square root of 1 minus that 0.886 again, divided by 8 minus 2, our sample size was 8. When we simplify this, we get a t-score of 4.68. Since this is a two-tail test, we get a t-critical that puts that 5% of the area in the two tails added together. So I use t.inv.2t 0.05 in the probability and 6 degrees of freedom to get this 2.4469 critical value. Because our t-score is outside the critical value, there's sufficient evidence to reject the null hypothesis. And in fact, what we're able to say is that there seems to be a positive linear relationship between tree height and trunk diameter. We can also use the p-value to test this, and Minitab provides the p-values for us. If the p-value is less than alpha, we will reject the null hypothesis and accept the alternative that there is a linear relationship between the two variables of interest.